In this lesson, we're going to talk about determining the domain and range of a function. The first question says, for each relation, state the domain and range and whether the relation is a function. So we look at this relation right here, clearly a set of ordered pairs. We'd like to know what the domain is. So what we can do is refer to each point individually and see where that point stacks up on the x-axis. So just view each point only as its horizontal component and see where it would be on that x-axis. And now treat the x-axis like a number line, and we see that it's a set of 7 discrete points, specifically -3, -2, -1, 0, 1, 2, and 3, and that's our domain. Now in order to determine the range, we do a similar thing and we look at only the vertical components. So this point right here has vertically with respect to the y-axis ends up on -2 on the y-axis. This point has a y-coordinate of -1. It ends up right here. This point right here ends up here on the y-axis. This point ends up here on the y-axis. This point ends up here on the y-axis. This point ends up here on the y-axis. And this point ends up here on the y-axis. And so we see that we've got these 7 points on the y-axis. And when we read the range, we read from bottom up. And so we see that our range would be -2, -1, 0, 1, 2, 3, 4. And there's our range. And to determine whether or not this is a function, look at the dots themselves, the original 7 dots. We see that they would pass the vertical line test. It's impossible to draw any vertical line that extends through the original 7 points more than once, and so therefore we have a function. Okay, we look at the next one now. This is a parabola that opens down, and so what we're going to do is first of all try to determine the range. Well, one way we can do this is to start at a known point, specifically the vertex, right there, and determine on the x-axis the horizontal component of that. And it would be right there on the x-axis. This point on the x-axis corresponds to right here. Now, as we proceed to the left from that point, we see that we start to fill in the x-axis in this direction. And parabolas are ultimately infinitely wide, so this parabola will ultimately go as far to the left as possible, infinitely far. Also, we can then go back to the vertex and start thinking about these points and where they would fit on the x-axis on the right-hand arm. And we see that they would extend to the right as far as possible, because ultimately this parabola, as we go down, 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 would become infinitely wide. And so we see that in terms of determining our range, the entire x-axis is shaded in. There isn't a point absent. And so therefore the domain is the set of all real numbers. Now to determine the range of this parabola, again we could start from a known point, the vertex. In terms of the y-axis, that vertex would end up right here. And now we can go down the left arm. And as we go down the left arm, in terms of the y-axis, we go down the y-axis. Okay? Going back to this known point of the vertex, we can go down the right arm. And as we go down that arm, we go down the y-axis again. And we see that what we've really got is a y-axis that's shaded in, including a y value of number 3, everything less than or equal to 3. So our range is y such that y is less than or equal to 3. Y is an element of the reals. And again, looking at the original parabola, we see that it passes the vertical line test. It's impossible to draw any vertical line that touches that parabola more than once. Okay, let's look at this next one. For this one, we see in terms of the x-axis, we see that we, at an x value of -5, we have an open circle. And then we proceed to the right all the way to an x value of +5. At an x value of +5, we put a closed circle. Then on top of that closed circle, we put an open circle at an x value of 5. Now, of course, putting an open circle over top of a closed circle is irrelevant because it's already been closed. And now we move to the right up to approximately the number, it looks like the number 12. And so we would say that our domain is equal to the set of all x. I failed to write that in, but we'll say the domain is equal to the set of all x such that negative 5 is less than x is less than or equal to 12. And x is an element of the reals. Looking at the y coordinates, we see that every single point on this upper line segment has a y value of 6. And every single point on this lower segment has a y value of 2. And so our range is simply the numbers 2 and 6. Okay? Now looking at this is a circle. It's pretty distorted looking. It's an oval here, but in the original note it's intended to be a circle. And in order to determine the domain, we want to start here and go all the way around the circle. And as we go all the way around the first half, we see that our entire x-axis from an x value of negative 5 to an x value of positive 5 is shaded in. And then we proceed all the way around back through the bottom, and we see that our domain is all the numbers, all the x values from negative 5 to positive 5, and x is an element of the reals. Looking at the y values, we could start at the top and we could go all the way down, which would shade in all these values on the y-axis. And then from here we could come all the way back up to the top again, and we would have all these y values shaded in there. And we would see that our range is equal to the set of all y such that, reading from the bottom up, negative 5 is less than or equal to y is less than or equal to 5, comma, and y is an element of the reals. Okay, sorry this is a little bit scrunched in at the end, but the range is the set of all y's such that negative 5 is less than or equal to y is less than or equal to 5, and y is an element of the reals. This is not a function because it fails the vertical line test, but this is a function because it passes the vertical line test. The only point in question would be this one right here, but we see that we have a closed circle above an open one, so in reality a vertical line right there would only hit this line segment right there. Okay? Now, next question says, state the domain and range of the straight line f at x equals 2x minus 3. Well, the first thing we could do is graph this a la grade 9. And we could see that this is an infinitely wide in both directions line. It covers all the x values to the far right and the far left. So because it covers all the possible x values in the real number system, our domain would consist of the entire x-axis. And so our domain would be the set of all real numbers. And similarly, it goes infinitely high and infinitely low, and it's continuous throughout. So in other words, it's going to shade in the entire y-axis because it goes infinitely low and it goes infinitely high. And so we could look at the y-axis and say our range is the set of all real numbers. And it's clearly a function because it passes the vertical line test. We could then look at the function g at x equals negative 3 comma x plus 1 squared plus 6. And we could try to determine the domain and range here. And we would see that the domain, starting from the vertex, we see that we go infinitely wide to the left. Even though it doesn't maybe look like it, it looks kind of narrow, it will eventually go infinitely wide. Parabolas have that property. And similarly, to the right, it will go infinitely wide as well. And so the domain is the set of all real numbers. And similarly, the range is a set of all real numbers less than or equal to 6. Our maximum y value is right there, and from here we go down each arm and we just sort of duplicate moving down the y-axis in a vertical sense. And as the y values get lower and lower, we go lower and lower down the y-axis. And so our range becomes the set of all y such that y is less than or equal to 6, and y is an element of the reals. Okay? Now our next question would be, what is the domain and range of the function f at x equals the square root of 2 minus x? Well, we know that no matter what goes underneath the square root sign, it has to be greater than or equal to 0. So in terms of the domain, we know that 2 minus x has to be greater than or equal to 0. Well, that means that 2 has to be greater than or equal to x, and reading that the other way, x has to be less than or equal to 2. So there's our domain. So our domain is the set of all x's, such that x has to be less than or equal to 2, and x is an element of the reals. And that goes back to the fact that anything underneath the square root sign, the entire quantity has to be positive. We set it greater than or equal to 0, and then we say, we solve for x and say x has to be less than or equal to 2. I said it has to be positive underneath. It has to be specifically greater than or equal to 0. In terms of the range, we can say that h at x represents our y coordinate. And so to say that y is equal to the square root of something is to say that y has to be greater than or equal to 0. Because the square root of something, no matter what it is, has to be greater than or equal to 0. So y has to be greater than or equal to 0, because y is essentially just the square root of something. And so our range is the set of all y such that y is greater than or equal to 0.